All right, so this is the chemical reaction screencast for objective 9 and 10. We're going to talk about basic equilibrium and equilibrium equations and how to write equilibrium constants. So the essential question for objective number 9 is, how is a chemical equation used to write the equilibrium equation? We're going to start off by watching a video clip. We will watch this in class, so you don't need to watch that on your own. Okay, so equilibrium constant and equation. We're actually not going to calculate these. We're just going to learn how to write the equations for them. It's not necessarily important for an introduction to chemistry class for you to learn how to actually calculate these things. That'll be kind of the next step of things. At equilibrium, the rate of the forward and the reverse reactions are equal. So that is the definition of equilibrium. And because of that, you can write an equilibrium constant. So the forward reaction, the reverse reaction, which this only shows the arrow going one way, which it should show the arrow going both ways. Here's a basic equation. You have, A plus B yields C plus D. And there's going to be numbers in front of those, the coefficients in front of them. So the coefficients are represented by the little a, the little b, the little c, the little d. If there is no number there, you know it's 1. So the equilibrium constant can be written as Kc. So C shows that it is in terms of concentration, which is what these brackets mean. So the brackets mean concentration, kind of parts, or it's going to be in moles, which you're going to learn what moles are next unit. But it's going to be in terms of its concentration in solution. So the square brackets show that it tells you the concentration of element C to the lower C power. So the concentration of this particular element or compound raised to the coefficient times the concentration of D to the little d, which would be to its coefficient. So the products go on top, and you multiply the concentrations together. They're going to be raised to the exponents of the powers of their coefficients. And you put the reactants on the bottom. So I would have A and B on the bottom side. Concentration of A times the concentration of B, and A is going to be raised to the little a, which would be the coefficient in front of it, and B is going to be raised to the little b, which is going to be the coefficient in front of compound B. We're going to work through some examples on how to calculate or how to write the equilibrium concentration equation. But once you get the hang of it, that you just put the reactant or the products on the top and the reactants on the bottom, it's fairly simple to write that equation. There is some information that we do get from the equilibrium constant. So if you know the equilibrium constant, meaning what is the concentration at equilibrium, the magnitude of that KEQ, the equilibrium constant, depends on the extent that the forward and the reverse reactions occur. If your KEQ is greater than 1, the products are favored over the reactants. If your KEQ is less than 1, the reactants are favored. So you can tell which reaction, the forward or the reverse reaction, is favored. If the KEQ is very large, essentially the reaction goes to completion of products. So the products are so favored that almost none of it goes to the reverse reaction. If the KEQ is very small, the reverse reaction goes to completion, or the reactants just don't react, so they stay that way. They do not form products at all. I'll show you some examples of this. So write the equilibrium constant equation for these examples. So right here, we're going to have, remember, our reactants on the top. So this would be concentration of HI to the second power divided by concentration of H2 times concentration of I2. And the KEQ, the equilibrium constant, is 54.8, which is a pretty high number. So which is favored, the reactants or the products? In this case, the products are definitely more favored. In this reaction, so writing the equilibrium equation, I would have concentration of CO times concentration of Cl2 divided by concentration of COCl2, and there's no exponents because there's no coefficients in front of any of these. The KEQ is 7.6 times 10 to the negative 4, which is a fairly small number. So in this case, the reactants are going to be more favored. So not very much product is going to be made. So if you were trying to make carbon monoxide in this reaction, this is not a good reaction to get that product. you might want to rely on another chemical reaction. And notice that they tell you the KEQs at different temperatures because most chemical reactions are temperature dependent. So you can actually calculate the values for the KEQ using the equation if the concentrations are known for all the materials, but I'm not going to take you to that step. That's the next step in this. So objective number 10 is determine the effects that temperature, agitation, concentration, and catalyst can have on chemical reaction rates. Really for this objective, the majority of it is going to be done during a lab activity. You guys are just going to compare what affects temperature, agitation, which would be stirring, concentration, and catalyst have on chemical reactions. So here's just a little bit of background information for you. Some reactions occur fast, some occur slow. The rate is the chemical kinetics, and some reactions you can speed up, some you can slow down, some you really can't change that much. They just don't react very well. So speed depends on concentration, temperature, the presence or absence of a catalyst, and just the nature of the reactants themselves. Like some things just don't react very well, like the noble gases. They don't react. The rate of the forward reaction will be much faster in the beginning when concentrations are high, and then it does slow down as you start to use up the reactants. So over time, a reaction will slow down. The forward reaction will. But as the forward reaction is slowing down, the reverse reaction will be speeding up. So the rate of the reverse reaction in the beginning is 0 because you have no product to react, but it will start turning back into the reactant as it's made. So you get the rate changing over time until it reaches chemical equilibrium. When it reaches equilibrium, the rate of the forward and the rate of the reverse stays the same, or is in its equilibrium state, so it's not going to change. Reaction rates, when we talk about reaction rates, we have to talk a little bit about collision theory. This should seem like common sense to you. Atoms, ions, molecules can react to form new products when they collide with each other. So as long as they have enough kinetic energy, there's enough movement, there's enough heat energy, there's enough thermal energy, whatever energy they might need. But as long as there is enough kinetic energy, they will react with each other. So how can we increase collisions? Well, we can increase the temperature. That makes things move faster. So if you make things move faster, you get more collisions, you increase the rate. That seems like common sense. If we increase the concentration, you just have more particles to collide together. So that's going to increase the rate. What if I took the particles and I made them smaller? Like if I grind something into a powder versus a big chunk of solid. I'm increasing the surface area. So because I'm increasing the surface area, there's, in theory, more collisions. So it will make the reaction happen faster. And then you can also use a catalyst, which lowers the activation energy. That increases the speed. So that has kind of the same reaction as the same effect as increasing the temperature. But the nice thing about a catalyst, it can be reused. So we're going to do these in the lab, and we're going to see if we can get reactions to go faster using this collision theory idea that if we allow them to collide more, we get more or faster reaction rates. So the summary for objective 9 and 10 is a 3-2-1 format. And like I said, we're going to finish the rest of this, or you're going to see the hands-on applications of this in a lab.